Our last major topic is something that is often called geometric optics. And the idea is, as the name suggests, you're just basically doing geometry, looking at the directions of propagation of light and seeing how those directions change and what properties of light change when you have light traveling from one material into another, or one medium into another. And we're going to be dealing with just some terminology here, so we should introduce it. We're going to be talking about wave fronts and light rays, which you probably already know what a light ray is, or at least have some idea what it means. But if we go back to thinking about radiation for a second, and we have, say, charges that are accelerating, such as in our antenna that we were doing demos with last week. Well, you have a, just run. So here's a wire that has an alternating current in it, and so we have charges accelerating upward and downward. And what I'm doing is I'm drawing the radiative electric field produced by these accelerated charges in the antenna. And of course, there's a distance dependence. The farther away you get, the lower the field gets. But it's also, if I change the perspective here, it's radiating in all directions. Now I'm just showing 6 directions. But you can see how the peaks, or the maxima in the electromagnetic waves, or in this case this is the electric field that we're drawing here, is that peak is spreading out in all directions. So there's a peak, and it moves away, and then another peak forms, and it moves away, and another peak forms, and it moves away. If I drew just a circle through those peaks that are propagating away from the antenna, then those circles that are propagating outward are called the wave fronts. Okay, so a wave front is just a line or a plane, and you could think about, or even a surface if you're spherically emitted in a spherical pattern, propagating outward. That surface goes through all the peaks a series of peaks in the electric field, electromagnetic wave. Okay, and we see that peak propagating outward. And then we've drawn essentially the rays here. These are lines that are perpendicular to those wave fronts. And so if this is our source, our antenna, then light is emitted in all directions except along the line of acceleration. And so we just draw the rays as perpendicular to the wave fronts. So here's a ray. A ray is just a straight line pointing in the direction of propagation, and it's perpendicular to the wavefront. Okay, so we can think about light traveling in straight lines, the wavefront's propagating out in the direction given by those straight lines. Okay, so rays and wavefronts, and we're going to talk about how these waves and rays and wavefronts change when you have light going from one medium to another. We talked about re-radiation last week, and how if you have electric fields, radiative electric fields that are incident on charges, like the electrons making up atoms in some surface, then those electrons will accelerate and they'll re-radiate. And for opaque objects, the re-radiation is such that it's canceling out any radiation from light sources on the other side. Okay, so we get complete cancellation, or what we call a complete destructive interference. It completely cancels out. But there are materials that light can pass through, right? We can see through windows. So there are transparent materials. And with transparent materials, things get a bit more complicated because you just don't have destructive interference going on. You have also possibly constructive interference. And so if you had, for instance, here's some material like glass, and you have a source of light over here, and you see the wavefronts coming through, and then they're incident on the glass. Well, that's going to cause the electrons making up the atoms in the glass to re-radiate. And so maybe here's an atom, and 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 here's an atom. And the wavefront, this is a circular pattern wavefront, right? So the wavefront will hit these atoms earlier than it hits these atoms, and so these atoms will start to re-radiate earlier. So if I draw the re-radiative wavefronts, the wavefronts due to the re-radiation, that may be already propagated outward some amount before these ones even start to re-radiate. And it becomes kind of complicated because you have all this re-radiation going on, but it's all sort of out of phase because the incident radiation isn't hitting these things all at the same time. So it becomes complicated, but the net effect is that you have to add up all the initial wavefronts and re-radiated wavefronts to get the new net radiative electric field. It must be the case that when you add it all up, it doesn't all destructively interfere. You must get some constructive interference as well. And so some wavefronts the net wavefronts can actually propagate through the material. Okay, if I can spell glass right. And so, at least for certain frequencies, there is a frequency-dependent effect here, but so visible light may be transparent, may be able to pass through the glass, but maybe not ultraviolet or other frequencies. So it depends on the frequency, it depends on the material, but essentially it's some complicated effect of a lot of radiation and re-radiation constructively and destructively interfering such that you get wavefronts traveling through. But the wavefronts change a little bit. And I'll show a little demo program to show how matter changes the wavefronts. So here's a wavefront from some radiative source, okay? And so we have these wavefronts going through air, for example. And so we track these wavefronts, and here they travel through air, and then they hit this glass over here, or some medium that's transparent. It's just shaded here to indicate it's different. And the result of all that constructive and destructive interference is that the net wavefronts change. They change in two ways. One is the wavelength actually changes. The distance between these successive wavefronts is smaller in the medium than it is out here. Okay. There's a direction change going on, and we can actually see some direction change if we draw these radial lines are the light rays. We see how the light rays, if we keep drawing them perpendicular to the wavefronts, then the light rays actually bend, at least at certain angles, when they enter into the medium. And the wavefronts are actually traveling slower. A single net peak in the wavefront moves slower inside the medium than it does outside, which brings up an issue about the speed of light. Isn't the speed of light a constant? Isn't the speed of light a universal constant? And doesn't the superposition principle tell us that no matter what we have in the way, the speed of light should be the same? You might have heard that light travels slower in various materials than it does in vacuum. You have to be careful about how you phrase the question. If I have a flashlight, for example, and here is a block of glass, and here's some detector over here where I'm going to detect the light coming in. There's really two ways to measure the speed of light. One is turn on the flashlight at t equals 0, and then measure the time when your detector actually measures light hitting it, and then the speed is going to be this total distance divided by that time. That should give you the speed of light. That should give you 3 times 10 to the 8th meters per second. no matter what's in the way, because the superposition principle tells us that this initial radiation comes through, and even though there's re-radiation, that initial radiation isn't affected by the re-radiation. It's still going to reach the detector at time t equal to d over c. Okay. But if you ask a different question, which is tracking one of these wave fronts, remember these wave fronts are the net wave fronts are the results of not just the incident radiation, but the re-radiation. That's a different question. And you can measure the speed of light differently by saying, how much time does a wave front take to move through from one point to the other? And so the speed of the wave front is going to be the wavelength divided by the period, okay, the period of oscillation of one of these sinusoidally oscillating charges. Or we could also write that as lambda times the frequency. And this thing will be different in different media because the wavelength, the distance between wave fronts is going to change. The frequency does not. The frequency doesn't change because these charges are still oscillating at the same frequency. But the wavelength actually changes. Okay? So we want to think about how these wavelengths change in different materials. And transparent materials have a property associated with them that tells you how much the wavelength has changed, and it's called the index of refraction. Index of refraction is given by the symbol little n, which is unfortunate because that's also the same symbol we use for mobility, or electron density, but we'll just have to deal with it. The formal definition of n is the speed of light in vacuum, 3 times 10 to the 8th meters per second, divided by the speed of the wave front inside the medium, okay, which is different. We see these wave fronts moving slower inside the medium. Okay? But again, because we can compare these two speeds, we can say the speed of light in vacuum is going to be the wavelength in vacuum times the frequency. And the speed of the wave front is going to be the wavelength inside the medium and when I say the word medium, I just mean some material that the light is traveling through. Okay, so speed in vacuum lambda in vacuum versus lambda in medium times the same frequency. Okay, and the frequency, of course, cancels out, and so you could also use this as comparison or a way to calculate the new wavelength. If you know the wavelength in vacuum and you know the index of refraction of the material, you can calculate the wavelength in this medium. Okay. Now notice it's a pure number because we're dividing a speed by a speed, so we just get a number. N, what are sizes of n's? Well, for most ordinary materials, pretty much everything we're going to deal with, n is greater than or equal to 1. Okay, so in vacuum, by definition, n is equal to 1. We just take the speed of light divided by the speed of light. In air, at standard temperature and pressure, n is approximately equal to 1.0029, which is often close enough to 1. Air doesn't really affect the wave fronts that much. Water, n is approximately equal to 1.33. And then various things, you have like plexiglass, for example, or n's about equal to 1.5. And other types of plastics, n's about 1.3 to 1.5, so it depends on the material. But those are some typical values, okay? So why don't we just try a quick question with this. a peak in the beam of visible light travels through polystyrene at a speed of 1.89 times 10 to the 8th meters per second. What's the index of refraction of polystyrene? This is really simple, but so you guys should be able to do this in, say, 30 seconds. It should be, and still we get some people who don't quite get it right. 1.59. Okay, but these are the people who are probably asleep and just clicking something just to keep going, but that's okay. 92% of us say that it's 1.59, which is correct. We just take the speed in light, divide by the speed in polystyrene. You can find the ratio. It's about 1.6. Okay.